something that would convert our input to our output, right? And in the frequency domain, we're not gonna worry about taking derivative, integral, and everything it's gonna be in the frequency domain. So basically, transfer function is something that if we multiply this frequency domain version of the input, we're gonna get the frequency domain output. Right, so let me just call this transfer function g of s. So if I multiply the frequency domain input by the transfer function, I'm gonna get the output. What's the frequency domain? It's basically the Laplace transform of the input, and this is the Laplace transform of the output. So based on this, you can see that the transfer function is basically output divided by input, right? It has a magnitude and it also has a phase, okay? So let me just call this one mg with the phase g. Now, can you guys think about how this relates to MO and MI, and how phase it's gonna relate to phase of O and phase of input? You can pause the video if you want to think about this. If you remember from your basic math working with phasors or complex numbers, you know that when you have two complex numbers and divide them, the magnitude of G, which is our system, it's going to be magnitude of output divided by magnitude of input. A phase of G, it's going to be, what is it? It's phase of O minus phase of I, right? So this is basically how we're gonna analyze the systems in frequency domain. We take the we take the Laplace transform or input, we find the Laplace transform of our system, or like we model the system in the frequency domain. The frequency response of the system, which is our output, it's going to be derived by multiplying the input by the transfer function. Okay, so that's one concept I wanted to remind you about this. And when you take the Laplace transform, we have our variable as s. So always remember that in order to convert to frequency domain, we just like do s equal to j omega. And omega is basically 2 times pi times the frequency. Okay, if this is the complex plane, this is real, this is imaginary. It means that like s can be anywhere here. It means that we are only gonna move s on the imaginary plane. These would correspond to different frequencies. Okay, so this is basically how we can find the frequency response of a system. Now, you guys have actually worked with transfer functions in your circuit course. This is one way of looking at the concept of impedance. Okay, so let me just remind you about something that you've seen before, but we're going to look at it a little bit differently. So let me make sure that you guys can see the whole thing. Yes, okay, so we have, let's say like we have a resistor here. right? This is V of R, this is I of R. And we have a capacitor, V of C, I of C. And we have an inductor, V of L, I of L. Okay. So for each of these three devices, three elements, we want to find like the relationship between V and I, the voltage and the current that goes through these elements. So for resistor, it's very simple. It's Ohm's law. Let me just actually do this in the time domain. So in the time domain, this is what we have. VR of t is equal to R times IR of t. Means that at each second, at each moment, the voltage and current, they're going to be related like this. If I take the Laplace transform of this one, assuming R is constant, we have that VR in the S domain is the same as RI R in the S domain, right? So they're exactly the same. For resistor, it's very simple. Now let's look at the capacitor. The capacitor, you guys know that I of the capacitor is equal to C dVc over dt. Again, these are in time domain. Let's take Laplace transform of this one. This is going to give us IC. Okay. If I take the Laplace, excuse me, Laplace transform of a derivative, you guys remember that it's going to be S times Laplace transform of voltage. Okay. So if I just write it a little bit differently, Vc of S is equal to 1 over Cs ICS. And let's do the same thing for the inductor. VL of t is equal to L dIL of t dt. Take Laplace transform. VL of S is equal to LS IL of S. Okay. So if we look at each of these elements as a black box, and we want to know if we apply this much current, what's the voltage across, right? So we want to model all of these elements using just a black box. We want to know like what's the relationship between V and I, right? So this is, we called it impedance. If you guys remember from your circuit course, this is called an impedance. This is basically a transfer function, right, that relates the output to input, where we define output as the voltage across the element and the input as the current that we inject to this element.